on image generative model, pre-trained image generative model. But this LRM is actually not based on image generative model. So task is very similar, just image to nerve regression. Very similar to Dream Fusion, right? Dream Fusion also tries to, although it is not regression, it is optimization. It optimizes nerve for each text prompt, but the input output are very similar, image to nerve. So Dream Fusion optimizes nerve by utilizing SDS loss function for each text prompt, but LRM is a large reconstruction model. Where is it? Large reconstruction model. So it takes images and outputs nerve, not generative model. You see the input output are very similar. Just the input is a single image and outputs are nerve so that we can render images from low variable point. The task seems very similar, 0 to 3, Dream Fusion, LRM, very similar. But the approach is very different. LLM is discriminative model, not generative model. It is trained to predict corresponding nerve from a single image. So it's very fast. Just that we just need single feed-forward pass using a neural network. So it is very fast. And input is nerve, image, and output is nerve. And it is based on explicit 3D implementation, nerve, right? Nerve is implicit, but it utilizes some 3D stuff inside of its model. But 0 to 3, it is generative model, not discriminative model. We know the Bayesian rule, right? So models that are interested in this kind of data distribution are called generative model, and models interested in this kind of label distribution space that is called discriminative model, right? This Bayesian rule. And it's trained to sample corresponding low-level images from image distribution. So the pre-trained, image generative model is pre-trained on exterior data set, right? Let's say we have huge amount of images, then the image generative model is pre-trained on such kind of exterior data sets, and then using such kind of pre-trained image generative model, 0 to 3 tries to fine-tune the pre-trained generative model to generate images from low variable points. And it's based on diffusion, so that means to get output, we need to sample. It is generative model, so basically we need to sample from distribution to get outputs, but this sampling process is especially slow for diffusion model because we need to do that iterative manner. The sampling process is iterative in case of diffusion model, which makes sampling a little bit slow. And 0 to 3, the output is image, right? Its output is not nerve. Output is not 3D representation, just image to image. Image to low variable point image. That is the input output formulation of 0 to 3, while LRM, image to nerve. So that once we reconstruct nerve, then we can render images from any viewpoint. So we learned there are various 3D representations, right? Mesh, volume, point cloud, nerve, there are many 3D representations. Which representation we need to choose to image to 3D reconstruction as a discriminative model? Mesh is good, but a template mesh has a fixed topology. We learned, right? So let's say we have sphere mesh topology. Sphere mesh topology cannot represent donut, this kind of donut, because they belong different topology. Sphere, we cannot make donut out of sphere, so that once we define some topology of a template mesh, then the expressiveness of model is limited by the topology of template mesh, so that mesh might not be very good option for this case. Volume is not restricted to a specific topology, but the problem is that memory is inefficient. We need to define high resolution volume to get details of object geometry, but that takes huge amount of memory. So volume might not be a good option. Point cloud, point cloud, actually it is not good for rendering. It is too sparse, right? Each point has no scale. So at that time, 3D-GS was not presented, so 3D-GS is not in the option. The remaining thing is NERF. NERF is good. It is good for rendering, photorealistic rendering, much more memory efficient than volume. Does not restrict to a specific topology of template mesh. NERF is good. But the problem is that the original NERF was defined for each scene. Remember? This is the original NERF. The input of original NERF is just a position and directional information. I mean, here the NERF is optimized for each scene separately, right? But we need model to take into account image as an additional signal here. But this NERF should represent near radiance field of this image. This image. We need to provide the input information to NERF. But the original NERF, it does not rely. I mean, it does not take some scene-specific information. It just takes a position and direction information, so that it is. I mean, just simply optimize for each scene separately. So how can we make NERF generalizable NERF that represent any object? Original NERF is optimized for each object, for each scene separately. So once NERF is optimized for some scene A, and it cannot be used for other scenes. That was the problem. But our goal is making image to NERF, right? Image to NERF, right? So that we need to make some modifications to the original NERF to make it generalizable to any image inputs. So how can we do that? So this paper used triplane. Triplane is another representation of 3D. Triplane is, as I remember, it is introduced in CPR 2022 of EG3D paper. It is GAN paper, efficient geometry aware 3D generative adversarial network, and in short EG3D. This is the qualitative result of this paper. You can see the images are good, but at the same time, we can get corresponding geometry in the 3D space. That was one of the main contribution of this paper, EG3D. And this paper utilized triplane representation. So what is the triplane? So as I said, the goal is to provide specially varying semantic information to MLPs in NERF. I mean, the original NERF, it only takes position and direction information, but this MLP should aware of some image information, right? The input information, input image information. But input image, there are many pixels, right? There are many pixels on image. There are many pixels. So how can we provide good pixel features to the MLP so that we can make generalizable NERF? That was the motivation of triplane. How can we provide specially varying? Specially varying means, special means this kind of space. We have space, right? We have many pixels on the space. It's specially varying. There are many, each pixel has different colors, different textures, so that we can define this kind of pixel colors as specially varying semantic information. So how can we provide this kind of specially varying information to MLPs? That is the motivation of triplane. One way is, for example, different color for each pixel in the input image. The original NERF cannot, as it only takes position, direction information. So one way is voxel. This one. We can define this kind of voxel where each voxel is optimizable. So each voxel, I have no idea which each voxel represents, but we can initialize voxel as a 0 value, and then we can just simply optimize this kind of voxels so that each voxel has latent information. We can perform trilinear interpolation from the voxel position, but we know the position, right? We know the position, so that when we design NERF, we know input position and direction information, and using such kind of input position information, we can perform trilinear interpolation from initialized volume, and then we can pass this kind of trilinear interpolated feature to the MLPs, in addition to position and direction and These are the original inputs of nerve, right? We can provide additional information of this kind of interpolated voxel features. Voxel feature means, for example, if we have an image, then we can, let's say this is blue color, this is red color, then we can interpolate some colors, right? There it might be purple color, it might be blue color, it might be red color. We can interpolate color from images. Likewise, we can perform interpolation on the 3D space, that is the trilinear interpolation, so that we can perform this kind of interpolation on the volume, so that we can provide additional information to MLPs, which is spatially varying information. Then MLP is aware of semantic information, spatially varying semantic information of this kind of volume. Then MLP is aware of, for example, which image nerve tries to represent such kind of information can be provided to MLPs. So anyway, voxel is the one way, but we know the drawback of voxel, memory inefficient. To get enough expressiveness, we need to define high-resolution voxels that makes memory inefficient. Then alternative is this one, triplane. Tri is, 3, right? So there are 3 planes. XY plane, XZ plane, YZ plane. There are 3 planes. That is called triplane. And instead of performing trilinear interpolation of the 3D space, we know position here, right? We know position, then we project XYZ position to XZ space, YZ space, XY space. Here you can see this kind of projection. We project, and then we perform interpolation on each plane separately. Right? That becomes this kind of features. We concatenate this kind of features and then provide this kind of original inputs, positional direction information. So there are 5 inputs, position information, direction information, XY feature, XZ feature, YZ feature. So there are 5 inputs to the MLPs. Then MLP is aware of spatially varying 3D information and positional direction information. So this is the triplane. We can define this kind of 3 planes to provide spatially varying information to MLPs, which is memory efficient than voxels. It can provide spatially varying information to MLPs. I guess seeing code is much more straightforward. These are pseudocode of triplane. So rand n is just making some random tensor whose shape is channel height and width. So that is just plane, right? Just like image, we have this kind of plane. So there are 3 planes: XY plane, YZ plane, XZ plane, and then the parameter means they are optimizable, like neural network weights. They are optimizable. And there are 3 planes: TXY, TYZ, TXZ. And there are 3 planes, and then this is coroning function. So that we have, this is coroning function. We have, let's say, for example, we pass XY plane, and our interest point is P. Then we pass the position of X and then position of Y. Then, for example, let's say this is TXY. P dot X. P dot Y. Then we can get the F1 here. If Px and Py are just integer, then we can just simply make a lookup table, just directly get pixel values from this plane, right? If Px and Py are not integer, if they are just floating numbers, then we can perform interpolation. So let's see, this is a 1 pixel. And this is, let's say, maybe P dot X, P dot Y, and let's say this is 8, 9, okay. And then 20, 19. This is y-axis, this is x-axis. and each pixel has values, each pixel has some colors, then we can interpolate using this kind of 4 neighbor pixels. If this is, px is, at the very center of these 4 pixels, then we can just make an average of these pixel values, right? This is called bilinear interpolation, and then we can perform bilinear interpolation to get f1 or f2, f3. That is called sample plane function, just a bilinear interpolation on the image space. And then we can just concatenate them. So that makes a single vector, and that becomes the input of MLP. Is it good? You can get it? Do you know bilinear interpolation? Good? So instead of, the original one, positional direction, so that the MLP, follow MLPs are not aware of spatially varying information. So this paper tries to provide additional information. And one way is making voxel, optimizable voxel, but that is memory inefficient. So instead of voxel, we are trying to provide, utilize triplane, 3 planes. And then, actually, this makes memory much more efficient. For example, voxel, then C, depth, height, W. This is voxel. And triplane, C, height, W, right? So if depth is larger than 3, triplane is always memory efficient. Usually depth is always more, higher than 3. The typical resolution might be 64. So 64, 64, 64. 64 is also not very enough, but let's say we are using 64 resolution. 64, 64. Triplane is much more efficient than volume, right? You can check. So that motivates triplane, utilizing triplane. Instead of using voxel, you can save lots of memory. And then here's triplane. This is architecture of LRM. Let's get back to LRM. And then here we have triplane. Remaining things are just, you can just simply check it. Not very complicated, just the image and convolution, and there are many transformer, not very difficult, I guess. Just self-attention, MLP, feature, linear position encoding, cross-attention, self-attention, MLP, and we have some new token, and then and then the good important thing is that we reconstruct triplane. Out of image, we reconstruct triplane. And then we perform bilinear interpolation for each plane. That becomes a point feature, right? And then we provide this one to MLP, which becomes, this is nerve, right? This is nerve. Oh, this is nerve. And then MLP's outputs are RGB and sigma. And then using this kind of volumetric equation, with slide from lecture 12, we can get low wave images. That is the entire pipeline of LRM. Maybe some of you guys are not familiar with self-attention, cross-attention in transformer. I guess you can learn such kind of things in other courses, but these are just kind of processing features. So we have some features from we learn convolution, right? And then we have some feature, and then self-attention, cross-attention are some attention mechanism in transformers. It's just another way to process features. And then the important thing is that we reconstruct triplane instead of just simply estimating mesh or volume point cloud. The first output triplane, and then follow MLP takes the features from triplane by concatenating 3 features from 3 plane, and then that becomes the input of MLP, and then such kind of framework is called NERV, right? So that each MLP outputs RGB and sigma, and then we can use this same thing, just a volumetric rendering equation, to get images from novel viewpoint or geometry of novel viewpoint. We can do such kind of stuff. And this is quite interesting approach. Original NERV, actually, it does not take any spatially varying information. So each NERV is optimized for each scene separately, and making generalizable NERV was not very tried at that time. But by introducing triplane in this kind of image to 3D reconstruction pipeline, this paper successfully made this kind of generalizable NERV. NERV can be used for diverse object, not only a single scene, single object or single scene. It can be utilized for arbitrarily object images by using triplane. First reconstruct triplane, and then this process is differentiable. Just bilinear interpolation, concatenation, all these processes are differentiable, so that gradient is, loss function is calculated for this one, right? We know NERV is optimized with image loss. Then the loss function is calculated for on this side. We render images in novel viewpoint, and then we optimize image loss, and the gradient is backpropagate through here, here, and then this deconvolution, reshape, and bilinear interpolation, concatenation, MLP, volumetric rendering. All this stuff are differentiable, so that gradient applied at the end of rendering novel view images, it can be backpropagate to even in convolution layers. So that entire system is end-to-end. This is called end-to-end. Input, output are connected with a single gradient path. That is called end-to-end system. This system is end-to-end system. Once we apply loss function, we calculate loss function at the output of the system, rendered novel view images. Gradient from rendered novel view images can be backpropagate to all these layers, because all these operations are differentiable, so that we can optimize all these systems only with image loss. And data set is very important. So they utilize combination of synthetic and real data sets. If they only use synthetic data set, PSNR is kind of measuring pixel-wise distance between rendered image and target image. The higher the better. So if they utilize only synthetic data set, then PSNR is only 15. Only use real image, also the PSNR is only 17, and by combining all of them, the PSNR increases to 19. So there can be, of course this is straightforward, but maybe we can ask some questions, like let's say it has maybe 100 million images or 10 million images, and this is called 110 million images. And what if we just simply use 110 real images? Then what happened? Or 100 million synthetic images? But there can be, there are actually many things in this table. What is the major driving signal of the performance improvement? Combination of synthetic, real, that can be one possible reason. Another one might be just simply using more images. We're not sure. So that if these numbers are just random numbers, are just randomly come up with these kind of random numbers. So but there can be many reasons of the performance improvement. Combining synthetic real image, that is the major reason, or just simply using more image, that is the major reason. I'm not sure, but I think using more image, the second one might be primary reason of performance improvement, I think. But So there can be multiple reasons why the performance improved. And here are some comparison to generative-based approaches. 1, 2, 3, 4, 5. You can see this name is also very funny. It is I think this is follow-up work of 0, 1 to 3. I mean they might share similar spirits. But as you can see, the qualities, this one is much better. This is not saying 3D-based approach is always better than generative-based approaches. There are always trade-off, and we cannot say one thing is always better than the other one. But at least for this one, at least for this paper, it beats the competitors, generative competitors. But as you can see, the backside of object, invisible surface, texture of invisible surface is not very good actually. You can see this kind of blurry texture. You can see also here, the visible surface is very good. Texture is very good, but as you can see, the invisible occluded surface texture is very blurry. But you can see that the object mainly consists of images without very complicated textures, and backside the object, for example, this kind of penguin, front part has very complicated texture, but back face of this penguin does not have very complicated texture. This is one way to appeal your paper. We can, on purpose, choose this kind of sample so that we can hide. I'm not saying this paper is not very bad. This is very good, but this is one way to appeal your paper. We do not have to show all the failure cases, right? We can pick such kind of samples so that so that we can say ours very strong, because we do not have to show this kind of all the failure case for all samples. And this shows the input image, and as you can see, this texture is not very sharp. You can zoom in. The texture is not very sharp. And there are failure cases. You can see the geometry and texture at the invisible part are not very good. Here, there's some blurry texture or some unrecognizable geometry. These kinds of things are unrecognizable geometry, right? Texture is a little bit blurry. The shoe geometry is a little bit off. But this one, does not rely on image generative model, right? You can check. There's no image generative model inside of this one. All these layers are just trained with the this kind of synthetic and real combination of synthetic and real data sets. There are no diffusion sampling. Just use convolution and transformer to directly regress triplane, and then MLP is also trained in a data-driven way. So this is one way, like a descriptive approach, to design image to 3D reconstruction. And there's no diffusion sampling. It is not generative model, so it directly regresses outputs that makes quite fast. Anything is unclear about this paper? Good. And I introduced this paper very briefly, maybe in last, I can remember clearly, but I think I remembered introduced this paper. So it takes VGGT introduced in this year's CVPR, yes, this year's CVPR. From multiple images, these are inputs, multiple images, it do feature matching, camera pose estimation, dense point cloud estimation in an end-to-end manner. This is also very interesting paper. So this is slide from lecture 9. We before midterm exam, we learned this kind of very complicated pipeline, right? We checkerboard, camera calibration, image matching, epipolar geometry, triangulation, structure from motion, multi-bit stereo. We learned all this stuff, but this paper, instead of doing all those steps, do them all at once with a single neural network. That is the value of this work. Instead of doing all this separated stuff manually, just giving multiple images, and then model outputs all this feature matching, camera pose estimation, and dense point cloud estimation, all this stuff at once, in an end-to-end manner. That is the value of this paper. And this shows the architecture of the VGGT. So they are, so input image, these are some tokenization and transformer attention. Just multiple images are tokenized and then passed to transformer, and then outputs just the camera pose, depth, point cloud, feature matching. So architecture side, personally, I'm not very interested in architecture side. So I will not introduce the architecture, but one thing is that existing transformer take patch level embedding. So for example, if we have this kind of images, height, width, instead of taking each pixel separately, it make a small patch, small local patch, and then each patch becomes pixel. Each patch becomes pixel. So instead of doing this kind of patch level embedding, the VGGT provide each pixel as each pixel separately instead of making a local patch. So treat all pixels separate tokens and pass every pixels for all images to transform instead of patch level embedding. Because geometry, we need sub-pixel accuracy. The patch level embedding, it might hurt some geometry accuracy. So to get sub-pixel accuracy, this paper passed every pixel of all images to transformers instead of patch level embedding. Of course, the problem is the memory. Then the number of token, there are too many tokens, right? But this paper addressed this kind of memory issue with alternative attention between global and frame attention. These are global and frame attention. Global attention, so you can see these small rectangulars are just a token, each pixel on the image. And then we can make attention of all pixels of all images. This is global attention, and frame attention is calculated for each frame separately, right? And this paper do global frame attention alternatively. Global frame, global frame, global frame. Where global attention is highly compressed because it takes too many tokens. So if we use some complicated global attention, then it might make memory issue. So that for the global attention, it uses very compressed operation, while in frame attention, it uses just a standard transformer. So designing this kind of two types of attentions, and global attention is very compressed, and this kind of alternative attention mechanism is the primary way to treat all pixels separate tokens, and then get sub-pixel accuracy. And just remaining things are just after many iterations of attention, it outputs camera extrinsic and just a per pixel depth map, point cloud, and feature matching. The data is very important. It uses, this is from paper, trained using large and diverse collection. These are public data sets and synthetic data set artists created assets similar to observers, their domain, and 3D notation. So for the video, they use lots of public data sets, synthetic data set of artists created assets, and 3D notation. For the real videos captured with our mobile phone or camera, we can use SFM or sensor capture. For some sensor, like if you use some sensor, it provides camera poses as well, so that if that information is available, then we can use them as a 3D notation. If it is not available, we can use structure from motion, right? We know structure from motion. From multiple images, if we run structure from motion, we get camera pose and sparse point cloud. Or synthetic engine. This kind of synthetic data set of artist created assets, that means all this, we know everything about 3D scene, right? Then we can use such kind of 3D scene as a 3D notation of rendered video. So these are the way that they collected data sets. From casually captured video, they use structure from motion, or some videos with some special devices. They use some sensor to get camera poses. Synthetic data set, they know everything about the 3D scene so that they can use such kind of synthetic engine to get 3D notation. As you can see, there are many data sets, right? There are many data sets. And these are results. So it even takes single view. Single view, it outputs, for each visible pixels, for each all pixels, it outputs point cloud so that we can rotate viewpoint. Of course, there are empty space, right? There are empty space. This space is empty because we output depth map for each pixel in the input image, and then we can just lift them and then rotate them. But that means there is 2.5D representation, right? We know 2.5D representation, right? We learned this. There are missing pixels, so that we do not know anything about the missing pixels, but at least for visible pixels, we can lift them in the 3D space, and then we can rotate them, and then we can back project to the 2D space. That becomes this kind of visualization. And these are the competitor. Result is visuality is much better. 2 view. This one is also the same. Here, this region is empty because this is not observable. This is not included in the input image. But at least for visible pixels, it outputs reasonable geometry shape, right? Good shape. And this one, we cannot recognize geometry. 32 views makes sense. Very good, I think. And time is, you can see, very fast. Because there is also here, you can note that there is no iterative sampling of diffusion. There is no diffusion. There is no image generative model. Directly regress, camera pose, depth map, point cloud, image matching. That's all. There is no denoising of diffusion. That makes very fast inference, right? Less than 1 second. Very fast. And these are also results are quite good, I think. This is famous landmark in Rome, right? And there are also lots of interesting visualizations. You can see visualization quality is very good, and I recommend your final project to include this kind of visualization. Of course, it might be fairly difficult. You need to raise your quality bar. You need to always raise your quality bar. Especially this kind of visual computer graphics, computer vision, you need to raise the quality bar so that you can, if you raise the quality bar, then you can see errors more easily. Then you can improve it. You make a good cycle. If you do not raise your quality bar, you cannot get errors. You think your visualization always good. There's no improvement then. You need to always raise your quality bar, and then you can get some errors in your visualization, and then you can fix this. There's a good cycle then. And here also, this is image matching result. A little bit hard to see, but this kind of all these points are consistently tracked in the 3D space. And using call tracker is, I think, the dynamic point tracker. Using this kind of one, they visualize point tracking result. And these are, similar to LLM 0 1 to 3, right? Just giving images of object and then get some low-level images. I think the quality is not very good compared to LRM. But this is also, this visualization also tries to show possibility of this work. Not only for scene level images, it can be used for object level images as well. And there are many tasks in this paper, right? Camera pose estimation, depth estimation, point cloud estimation, fit image matching, tracking, they argue that this kind of multitask learning is beneficial. Using all this task produces best result. They are saying, so I think ACES is acceleration error. So anyway, using all this multitask learning gives best result. Camera pose estimation, depth. I guess it makes sense because the camera pose estimation, depth estimation, image matching, point cloud estimation, all these tasks are relevant, I think, right? For the tracking, we need to know camera pose and depth estimation. For the depth estimation, we need to know camera and tracking. All these tasks are complementary relationship. They are not separate. They are not entirely separate tasks. So that multitask learning might be beneficial for each task. And but I guess last week, depth anything from ByteDance was introduced. This is also very similar to VGDT, recovering visual space from any views, and you can see visualization. Let me refresh this. This visualization is really good. I wanted to show you, but I'm not sure I can. I recommend just personally visit this website and see this visualization. Visualization is very good, and the result is also very good. And the task is very similar, just from multiple images. It offers matching, depth map, and point cloud, do all this stuff at the same time. You can see this video. Here, the left top two persons are running. We have depth map, and then we have structure from motion style visualization at the left bottom, and right one is reconstructed tracking result. Really good, right? This kind of depth anything from ByteDance is, I think, even better than VGT. And even it can handle a dynamic object. You saw the two persons are running. They are dynamic objects. And ByteDance is owner of TikTok, social media, and ByteDance is doing very good job these days. At the early of 2020 or 2021, ByteDance was trying to do some 3D stuff. At that time, it was not mature, but these days, like last year or this year, ByteDance is doing very good job at this kind of, not only for 3D, but video generation. They are doing very good job, I think. And then, okay, anything about VGT? Anything is unclear? Good. And actually this is original not included in the original plan, but some of you guys know SAM3D is introduced last week, I think. So I just tried to introduce this one. This is also shows very good result for 3D reconstruction. This is from Meta, and this shows the YouTube video.
Introducing SAM 3D, 2 new models for image to 3D transformation. Generate a 3D model for any object in an image. Get geometry and textures for all angles of an object, even the parts you can't.
아까도 비디오 안 보였어요?
아까는 보였어요.
아. 이게 왜 안 보이지?
Or introducing SAM 3.
I just recommend you personally visit this YouTube video website and see this video. The results are very good. There might be some, yes, static image result. This image and this is 3D reconstruction result, and you can see other qualitative results like where is it? You'd better watch the video. These are some image to 3D reconstruction results. You can see these kind of things. This is the one screenshot from video. And yes, 3D reconstruction from a single image. Meta Sport Intelligence Lab. Sitendra Malik is the legendary faculty member in Berkeley. He's very senior, one of the first generation of computer vision. He might be a 60, maybe. He's a 60, 65 years old, maybe. Architecture, there's not very, special architecture, but one interesting thing is that it is based on both descriptive and generative models. So the first stage, this is the stage 1, and this is stage 2. Stage 1, descriptive. Stage 2, generative model. We will see this one. So stage 1, this one. Stage 1, coarse geometry reconstruction. So from image, and mask might be from binary mask, I think. Anyway, from image, it outputs voxel coarse geometry. And this is the similar thing that we learned, like a LRM or rigidity. There's no image generative model, just the transformer and outputs voxel, directly regress voxels. And there are some rotation translation scale pose. It reconstructs 3D volume from a single image for each object separately. And this is discriminative approach. So directly regress voxel from image. There's no diffusion, there's no denoising, there's no iterative sampling. This is the first stage, stage 1. And for the stage 2, this one is stage 2. Stage 2. Then there is a generative model. Flow transformer is a generative model. Based on generative model, sample similar fine geometry and texture from data distribution, condition on image and coarse geometry. So generative model, it assumes some distribution, right? We have some distribution, and condition on image, it tries to sample some point from distribution, right? Here we have diffusion stuff. Diffusion stuff, sampling stuff is included in the second stage. So given coarse geometry and image, it tries to sample some fine geometry. Fine geometry. Fine means detail geometry and texture from data distribution. That is second stage. So there are 2 stages. First stage, image to voxel, discriminative approach. There is no diffusion stuff at all, just directly regress voxel. Second stage, use voxel as a additional input and image, and condition on image and reconstruct the voxel. It tries to sample detail geometry and texture. So there are mesh and 3D-GS. Mesh. So we know that there's a topology issue, right? Mesh, once we define a topology of a template mesh, then all the reconstruction might be restricted by the topology of the template mesh. That was the one drawback of introducing mesh in your network. But this work tries to avoid this issue by first estimating SDF. We learned SDF, right? Sign distance field. Sign distance field is, for example, this is, let's say, the surface. Surface, and for each position, it outputs shortest distance to surface, and the interior of surface is minus sign. Outside of the surface is positive sign. So it first outputs SDF, recover SDF, because SDF is not restrict with some specific topology, SDF like a volume style representation. With VAE is from this work, and then it performed zero level marching cube. We learned this one also. We have SDF, and then we are trying to get a surface whose SDF value is 0. That is zero level marching cube. So we first recover SDF with the flow transformer and VAE of this work, and then perform zero level marching cube to get mesh. So that by using SDF as the intermediate representation, we can avoid this kind of topology issue. Even we use mesh in neural network. That mesh is the one thing, and the other one is 3D Gaussian splatting. We recovered K Gaussian for each voxel grid. So we have voxel, right? We have voxel, and for each voxel, we define K. K might be 8, maybe. K Gaussians for each voxel, so that there are depths, height, width, K Gaussians. There are total this amount of Gaussian, and then the Gaussian decoder just try to estimate Gaussian features like mean, rotation, scale, opacity, and color. That is a Gaussian decoder. And here, due to nature, so here we use flow transformer generative model. That means we assume some distribution. We assume some data distribution, and we sample some point from the distribution. That is generative model's nature, right? Not reconstruction. There are some gap between input image and reconstruct 3D data. This looks similar to this image, but if you see detail, you can see clear difference between image and geometry. You can see the video, and the video is actually very fast. I think that is made on purpose to make people not see this kind of difference. But you can stop the video and then see difference between image and reconstruct a 3D scene. You can always see the meaningful difference between input image and reconstruct 3D scene. You better watch the video. In case of this screenshot, you can see clear difference actually between image and reconstruct a 3D object. But very similar, but I mean a little bit different, but very similar. But still good. Data set is always issue. These days, especially architecture side, everybody's using transformer. So also, I personally am not very interested in architecture side, but so data set and representation, loss function, such kinds of things are much more important than architecture. So for the data set, how can we collect massive scale of data that covers almost all kinds of objects? So there are many objects, right? This one, bottle, microphone, pencil, there are many objects. How can we collect massive scales of data that cover almost all kinds of objects? That is impossible. But they come up with some smart way to address this issue. So the training consists of 3 stages. The first one is pre-training of synthetic data. The 3D artist made many assets, many 3D object assets, and then we make a virtual cameras surrounding 3D object, and then we render images. Then we can make image to 3D pair, right? We pre-train the network on synthetic data. That is the first stage. And second one is mid-training. We have synthetic 3D geometry and texture, and then we can render it to some camera space, screen space, and then let's say we have real images. These are background is real images, right? Then we can just simply copy and paste rendered synthetic image on the real image, right? It might be semantically implausible. You can see chair is up, on the house, or the tractor is in the midair. So semantically, this kind of copy and paste does not make sense, but it tries to reduce the domain gap between synthetic images and real images. Just render synthetic images and then just copy and paste it on the real image, and then train. So the background is filled with real images, right? Instead of this kind of white background is filled with some real images. And then we continue train with this kind of combination of synthetic and real images. And the final one is This one is very important. This kind of pre-training of synthetic data and copy and paste, these are actually very typical things, actually. Tried many times in previous work, but this one is, these days people try to use this kind of weak supervision. This is human preference with model in the loop. Model in the loop, MITL. So the strategy for this model in the loop is that we have pre-trained model, right? We pre-train on synthetic data, we pre-train on combination of synthetic and real images. The model might produce some not very accurate, but some plausible 3D object, right? Then let model do 3D reconstruction from real image without, images without 3D ground truth, or let model do 3D reconstruction, and then we have some candidates of the 3D reconstruction, and the human annotators let human annotators choose whether which 3D reconstruction is good or not. So we let human annotators choose which one is good, which reconstruction is good. And then we use such kind of chosen one as a pseudo ground truth, not very accurate ground truth, but based on human preference, we use such kind of chosen ground truth as a pseudo ground truth, and then use such kind of chosen pseudo ground truth for the weak supervision signal. That is the third training of this system, right? So by doing this kind of using pre-trained model, we can get pseudo ground truths from lots of real images, so that we can secure additional real-world image and 3D pair data set. We can use such kind of data set to further train the system to get better result. And this one shows the mesh reconstruction. TriPoSG, I think this one is widely used. As you can see, images occluded by some object, so that previous work always outputs only partial of object, but here it outputs full 3D geometry. Here, human is occluding this object, and only partial. In real world, always occlusion always happens. So this work tries to avoid this issue. Mesh reconstruction results is, much more better. Even for multiple object cases in a 3D space, it makes a consistent, coherent position in the 3D space. And this is about data. So I introduced pre-training, right? Pre-training on synthetic image, and mid-training on synthetic object pasted on real image. That is this one, pre-training and mid-training. Here, the higher the better, F1 score. If we use only pre-training, F1 score is only 0.13, not very good. If we include mid-training as well, then F1 score was better. We get 0.17, and then these are third stages. The SFT is supervised fine-tuning. MITL is model in the loop. Supervised fine-tuning, where the target 3D is chosen or lightly edited by usual annotator from model-generated candidates. So let's say we have real images, and then we let model do 3D reconstruction, and usual annotator, not artist, like us. We are not artists, right? Usual annotator choose which one is the best one, or make small modifications of the reconstructed result. That becomes another ground truth of the real image, and use such kind of chosen ground truth or lightly edited ground truth as additional ground truth for the training. That is supervised fine-tuning. MITL is model in the loop. And DPO is a short word of direct preference optimization. And here, preference alignment, where pairs of model-generated candidates are ranked by usual annotator. So usual annotator is, like us, like some people who are not artists. So we have some candidates of 3D reconstruction from models, and then we make a rank. Which one is the best one? Which one is the worst one? And then we use such kind of rank annotation is another supervision signal. That is DPO. Artist, all these things are done by artist, expert artist. So supervised fine-tuning, MITL, we have some chosen pseudo ground truths from model reconstruction and then used for fine-tuning. It increases F1 score. And then we have DPO. We make a rank from candidates from models reconstruction and then use such kind of rank information as a additional fine-tuning signal. Then F1 score increases. And here remaining things are done by artists. F1 scorecard increases. So that using all this kind of training stages, it finally reached to 0.23, which is much better than initial pre-trained one. Pre-trained only on synthetic images. So far, so let's summarize, make a summary. So discriminative approaches like LRM, VGT. So we need to make a clear difference between discriminative generative approaches. They have strong, pros and cons for each approach. Discriminative approaches like LRM, VGT, they only use knowledge in the training set for the targeting task. This shows the example. If training set consists of front and back view images, and there's no side view images, the discriminative approach cannot reconstruct side view images. That's true, right? Let's say, imagine you're training LRM and VGT, and your training set only consists of front and back view of images, front and back view of object, front and back view of scene. Then your model cannot reconstruct side view images because side view images is not included in the training set. If training set consists of all the images, then your discriminative approach can reconstruct all the images. This is the major difference between generative model. Generative model can use exterior knowledge, which is called data distribution. Imagine you're using image generative model, like a stable diffusion, anything that is trained on exterior data set. We have lots of images, lots of videos. We learn prior distribution of such kind of image and video. And then let's say you're targeting image to 3D reconstruction, the same task. And you're assuming your training set consists of front and back view images. Generative model can hallucinate side view images. That is the clear difference between discriminative and generative approaches. Discriminative approach, it only uses knowledge in the training set. And then if your training set consists of front and back view images, it cannot reconstruct side view images. But generative model, although your training set only consists of front and back view images, as we have some data distribution, right? We have some image distribution, so that although we provide supervision for front and back view images, it can hallucinate side view images. This model has not seen any side view images from this data set, but it knows some image distribution, so that it can sample some plausible side view images from the data distribution. That is the clear difference between discriminative approach and generative approach. That means, for the side view image reconstruction, front and back view images are kind of weak supervision, right? We are interested in side view image reconstruction, but while we only have is front and back view images, then this kind of weak supervision signals are still informative if we are using generative model. For example, human preference. We use this kind of DPO, right? Human preference. We make a rank on the candidate of 3D reconstruction, and then use such kind of rank information as additional supervision signal. For the discriminative approach, it is not possible to use this kind of rank information of this supervision signal. But generative approach, weak supervision is still informative. That is the clear difference between discriminative and generative approach. It seems like generative is always better, but it's not true. For this kind of exterior knowledge, the data distribution should be very strong. Before diffusion models, this kind of data distribution was not very strong. VAE, GAN, normalizing flow was not very strong. So this kind of approach was also, already possible even at the time, but exterior knowledge, data distribution was not very strong at that time. So that this kind of, although this generative model have this kind of strength, always descriptive model always achieve better result than generative model. But these days, exterior knowledge, data distribution is getting better and better, and so that in some cases, or in many cases, generative model is performing better than descriptive models, because this exterior knowledge, data distribution is getting very better, much better than previous ones. And for the time, many people are actually making diffusion fast, but compared to the descriptive approach, usually slow, because for the diffusion, we need iterative sampling so that it makes the inference a little bit slow. Then, time is also different, but the major difference is that whether we can use exterior knowledge for the data set sampling, output sampling, or just use knowledge in the training set so that we cannot hallucinate unseen object. So that is the reason why we have this kind of, where is it? Empty space, rigidity, discriminative approach. You cannot use exterior knowledge outside of training set. Then there's no way to reconstruct this kind of empty space, right? That is the reason why rigidity outputs this kind of empty space. If this is based on generative model, it can hallucinate this kind of unobserved images. There can be some grass plane or anything can be. We can hallucinate many possible 3D stuff if we can use generative model, but descriptive approaches, it cannot hallucinate. That is the difference between descriptive and generative model. Anything is unclear? Good. Let's check the attendance and finish. And we have the final exam announcement. We will have, I made an announcement at the LMS. We will have final exam on the December 16, same time, but the place is different. You need to note that. Place is different. 미래기술융합관. 미래기술융합관. 101 auditorium. You can check the announcement in the LMS. And remaining lectures before final exam, we'll briefly study robotics, 3D kinematics, forward inverse kinematics, reinforcement learning, physics-based simulator, visual language models. We cannot cover all this detail. We briefly cover some robotics stuff.